Hey, grade 12s, we're going to take a look at how we can use some of these redox reactions that we've been looking at and practicing with balancing. When we consider any redox reaction that we've balanced or looked at so far, what we've done is shown that electrons have been transferred from one atom onto another one. So we have this flow of electrons that is happening. And a flow of electrons is electric current. So one of the most wonderful things we can do with electrochemistry is that we can use chemical reactions to make electricity. Also, we can use electricity to make chemical reactions. We call it electrolysis when we use the electric energy to make a chemical reaction happen. This is what happens when you charge your cell phone batteries. Electrochemical cells use chemical energy to make an electric energy happen. So for example, when you use your cell phone, you're using a chemical reaction in the battery to generate electricity that you can use. So in any redox reaction, my electrons are only going to be either completely or partially gained or lost. So in an electrochemical cell, if I want to make a battery, I'm actually going to need to use those where we have a complete gain and loss. And that's really important because I'm going to need those electrons to eventually flow through a wire so I can use that current for something useful. Now in these first reaction with carbon and oxygen reacting to make carbon dioxide, this is a covalently bonded substance. And so that's a partial gain and loss of electrons. We don't actually ever have carbon losing 4 electrons. It just kind of lends them closer to the oxygen. However, in the sodium and chlorine reaction, this ionic reaction, sodium completely gives off its electrons and chlorine completely gains them. So this is the kind of reaction that's useful when we're making a battery. When we consider this ionic reaction, we can actually separate it to the 2 half reactions. We could start by assigning our oxidation numbers to each atom in the compound, and we'd see that sodium is losing electrons to become sodium ion. I write that like this. My sodium atoms become sodium ions and 2 electrons. So we can see that the electrons have been separated from the atom in the end result. The chlorine, however, that went from 0 to -1 has gained electrons, 1 on each chlorine, so it's going to gain a total of 2. So this is how we show the gain of electrons. So when we're losing electrons in an oxidation, we're going to have my electrons on my product side. When I'm gaining electrons in my reduction, we show the electrons being gained, they're coming in as reactants. These are the half reactions that are involved in the pushing of these electrons. And if I can make these electrons go through a wire, I can actually use that energy to power a device. Now, this flow of electrons is usually called electric current. And when it's going through a wire, that's metallic conduction. When that current flows through a solution, and a lot of these reactions will have to happen in a solution, then we call it ionic conduction. Regardless of whether the electrons are flowing through a wire or a solution, the current is in one direction. It is one way, and we call that direct current. Now, there are reactions where this just happens all on its own. For example, your cell phone battery, when you use it all day, that reaction just happens, and so that we can use that energy. But in some reactions, like when we charge the battery, we have to force those electrons back in a way they don't want to go. We could use a battery, we can plug it into a wall, but we're going to have to push those electrons, kind of like pushing them up a hill. This is an example of electrolysis where I'm actually pushing electrons. The negative terminal of the battery is the place where there is a buildup of electrons. Now I'm talking about actual current here, not conventional current. So in the automotive industry, they quite often label these opposite. But from the chemist's point of view, the reason the terminal of the battery is negative is there is an abundance of electrons there. These electrons will be pushed off of the battery, and they will flow down this wire onto this electrode that we call a cathode. And at the cathode, electrons are going to get forced onto some species in the electrolyte. Because somebody is going to be gaining electrons, we will have reduction happening at that cathode. Reduction always happens at the cathode. Now, in the solution, there will be some kind of species as well that is going to have electrons being pulled off of it. And so these electrons that get pulled off are going to get attracted to this positively charged strip called the anode, and they're going to get pulled back, and they're going to get pulled back into the battery. So because the anode is pulling electrons off of things, we will say that oxidation is happening at our anode. Reduction always at the cathode, oxidation always at the anode. I want you to remember that. Reduction is at your cathode, and oxidation is at your anode. Now, the way I remember this in my mind, one of my crazy little mnemonic devices, is that reduction and cathode are both starting with consonants. Oxidation and anode both starts with vowels. You can use any kind of way to remember this, but it is important that you remember that that's what's going to happen. So what's actually going to happen when I have sodium chloride and I force this reaction to happen by running electricity through it? Sodium chloride is just table salt, and we know that it is never going to spontaneously just decompose to form sodium metal and chlorine gas. That won't ever happen on its own, and thank goodness for that. But if I run enough electricity through it, then I can get this reaction to happen. So what I'm going to start to do is I would start by melting, by heating up my sodium chloride till it's very, very hot, so that the sodium ions and the chloride ions could float freely from each other. And then I would put in a source of electric current, and we can see that I have labeled my negative terminal with the shorter of the two in this cell notation, and the positive terminal is the longer of the two lines. And that means that any electrons that are coming will be coming off of the negative terminal and going down into this molten sodium chloride. Now, as that electron goes down into the sodium chloride, who's it going to attract? Well, obviously the positively charged sodiums are going to be attracted to the electron, and the positive on the sodium and the negative on the electron will cancel each other out, and we will end up with just plain old sodium atom here. So we can see that what's happening at my negative terminal is the gain of electrons, where sodium ions gain electrons to form sodium metal. And I would see sodium metal plating up on that electrode. What's happening at the other side? Well, at the other side, we have electrons being pulled out of something in this molten sodium chloride. Now, who would be losing electrons? Well, we have these chlorine ions, and we can see that each of these chlorines is going to have a negative charge on it. And as they come up to, the electron, to the electrode, we will see that they approach the electrode and that the electrons get pulled off of that chlorine and get pulled back into the battery. And so we can see that each of these chloride ions has an electron come falling off. There it is, right here. And when two of them do that, when we have two chlorines doing this, and they get together, we form chlorine gas, diatomic chlorine. So this is what's happening when I run electricity through sodium chloride. Now let's take a look at what happens if I run electricity through water. This is the same idea. Again, I have a negative terminal and a positive terminal. I've just bent my electrodes here so that we can put some test tubes over this and collect the gases that are formed. When I look at water, I can see that it's made up of hydrogen and oxygen. So water can be broken apart to form hydrogen gas and oxygen gas. And again, we know this doesn't happen on its own. Water never spontaneously undergoes this chemical reaction, but we can force it to go if we give it enough electricity. So to figure out what's happening, let's take a look at what the oxidation numbers would be. Hydrogen here gets a +1, oxygen -2, and as products, they're going to have oxidation numbers 0. So I can see that the hydrogens in the water go from +1 to 0, which means that the oxidation number's gone down, which means that we've been reduced. So here is my reduction. We can see that the water has got a reduction where we formed hydrogen. Well, reduction we know happens when we gain electrons, and electrons are gained at the negative terminal. So at this negative terminal, we've got electrons being forced down into the water. Down they come into the water. And what they're doing is they are attaching themselves to hydrogens. So I can see here that I'm going to have an electron attach itself to a hydrogen here, and also on another water molecule to a hydrogen there. And that's going to break the water molecules off right here. So each of these hydrogens, which are more like a +1 charge because the electron's so far away from the oxygen, is positively charged relatively there, negatively charged relatively there. Not all the way positive and negative. This is a covalently bounded compound. But the electrons are going to attach themselves to one hydrogen each. And then those two hydrogens are going to get together to form hydrogen gas. And the hydrogen gas will bubble up. So the bubbling that's happening in this test tube here is going to be hydrogen gas. And we're going to have an abundance of what's left over, hydroxide ions floating around in the solution on this side of the reaction. And because of that, if we were to test the water near the negatively charged terminal, the cathode, we would see that it was basic. Well, what's happening on the other side of the cell? Well, on the other side of the cell, we know that we're going to be having an oxidation. We can see that oxygen is going from -2 up to an oxidation number of 0, and that means that it must be losing electrons. So each of two oxygens is going to be losing electrons. We're going to be losing electrons, will be coming off here. We're going to be losing electrons, they'll be coming off here. And when those electrons come off, it essentially splits this molecule up. We're going to have these two oxygen atoms hook up together to form my oxygen gas, and then I'm going to have these 4 protons left remaining. So I can see that when I take a look at what's happening on the other side, that electrons are being pulled out of the solution, off of something. We can see they're being pulled off of water, and they're being pulled up this electrode towards the positive terminal on the battery. I know that oxygen gas is being formed, and I would see that protons are starting to accumulate in the water near this terminal, and that at this terminal we would be seeing a positive charge at energy. My solution would look acidic. Okay, let's take a look at how we could put this all together. So remember up here, we have already labeled each oxidation numbers. We know that each of these hydrogens has an oxidation number of +1, and the oxygens have oxidation numbers of -2. I also know that I'm going to add an electron onto this guy and an electron onto this guy. So what we're seeing so far is that we're going to have 2 water molecules are going to gain 2 electrons. And what's going to form is hydrogen gas, H2, and we can see that hydroxides will form. Because we took 1 hydrogen off of each water molecule, we get 1 hydrogen gas, but that resulted in 2 hydroxides being formed. Let's take a look at what's happening on the other side as far as writing a half reaction. Again, we know the oxidation numbers. We figured them out before. We have -2 on each of the oxygens, +1 on each of the hydrogens. At this point, electrons are going in. So I see electrons are going to be, this point electrons are coming off. I've got 2 electrons that can be lost from this water molecule. And I have another 2 electrons that can be lost from this water molecule. And that's what forms our oxygen gas. So I can see that I've got 2 water molecules that are going to lose 2 electrons. I'm going to write this wrong here just for a moment, just show you what's going on. We never would write minus normally, but we'll fix that in a second. When they do that, we form an oxygen gas, and we've now released 4 protons. Now, we can't actually write minus on a reaction, so to correct this, what I'm going to do is I'm going to just move these electrons to the other side and say that 2 electrons on each one, so we're going to have a total of 4 electrons because it's 2 off of each water molecule, 4 electrons. And now this reaction is balanced for the other half of the reaction, the oxidation half of the reaction. So we now have water molecules that are gaining electrons and water molecules that are losing electrons. Let's rewrite these and show how they add up together. All right, so I've just recopied the 2 equations that we had on the screen so that we can more readily put these back together. We can see that I want to make sure my electrons will cancel. So I'm going to start by multiplying my gain of electrons, my reduction half of the reaction, by 2 so that my electrons can cancel. So multiplying everybody by 2, the reaction changes to look like this. So we've multiplied that by 2, and now my electrons, 4 electrons in cancels 4 electrons out, and I can rewrite this. We can now add this together. So on the reactant side, we have 4 water molecules, and the electrons are gone, and we have another 2 water molecules. So we're going to have a total of 4 plus 2 is 6 water molecules is reacting to form. You can see on the product side, 2 H2s plus 4 OH minuses plus O2 plus 4 H pluses. Now at this point, there's one more thing I can do. I can see that this 4 hydroxides and the 4 protons are going to react together to make 4 water molecules. They'll just hook up. And then those 4 water molecules will cancel 4 of the 6 to have 2 left over. And at this point, we're left with 2 waters reacts to make 2 hydrogens and an oxygen. Okay. There's one more thing I want to show you. What would we have happen if we were to put my electrolysis apparatus into salt water? How would that form? We can see there's 2 possible reductions. We can have electrons attaching themselves to the sodium or to the waters, which will be easier because electrons will always follow the easiest path. Also, there's 2 possible oxidations. 2 places we could remove electrons. Will it be easier for the electrons to be removed from the oxygens in the waters or from the chloride ions that will be floating around in the solution? I'm going to have you guys research this one yourself. And what I want you to do is to go to your textbook and take a look at brine. Now, brine is just salt water. Take a look at the products that are formed and see if you could figure out which of the reactions were preferred, which of the reactions in the oxidation was chosen, and which of the reactions in the reduction was chosen. I also have a YouTube video for you to watch. It's listed here in your notes, and I will link it below this video. And then I have a whole series of questions for you guys to do in your workbooks. They're about pages 18 to 22. And I know that sometimes the numbering in the workbook section doesn't really match, so if you look right after the balancing worksheets that we did on simple ratios and splits, you'll find these worksheets called Assignment 5 Review, and there are 16 questions with their answers recorded over those 4 pages for you to practice electrolysis.